Okay, so we had, as a commercial company, we had preset objectives that my board of directors instructed me that if I'm going to develop a variety that is resistant to TR4, I have to meet certain conditions. And among these conditions were that, first of all, the variety should be a Cavendish variety. As a commercial company, we don't cater to, unfortunately, to local market producers. We cater mainly to companies that produce the Cavendish variety for the export market. So we focus on the export market only. We also produce a little bit of plantain, but the majority of the products of Rohan Meristem is Cavendish. So I had to be restricted to Cavendish varieties. The second parameter that I was instructed by my board of directors is that we will not aim for a tolerant variety. We did not want a tolerant variety. We want a resistant variety or nothing else. So my goal is to develop a totally, fully resistant variety, not a tolerant variety. This is the objective set by my board of directors. The third objective was that the variety that we are going to develop will be stable and sustainable. Okay? So in other words, stable, that the trait will last for a very long time. And sustainable, meaning that we don't have to combine the resistance with a chemical treatment or any other procedure in the field. It has to be sustainable. In other words, it has to rely on genetic resistance only. The next point is, as I said before, that it should be useful for or appropriate for the export market. So that being said, it has to compete with the other Cavendish varieties. So, of course, that's not easy because the other Cavendish varieties, as you know, are very well suited for the export market. Okay, next parameter is that we will meet yield and quality criteria of the export market. So it's more or less what I said before. And the last point is we have to expedite this research. So when we started from ground zero, and we knew that if we do not reach the goal within 3, 4, 5 years, the world will start really suffering from the existence of the disease around the world. So I had to do it very quickly. Okay, next I want to speak a little bit about how do we validate our material in the field in order to give you confidence about this variety. So the parameters that we are using is, first we pre-screen in a laboratory that has the expertise, the world expertise in screening material for TR4. This is the laboratory of Professor Gert Kema in the Netherlands. The second phase is we take the material that we chose from after the screening and we put them in field trials in a region that is very heavily infected with the disease. So we don't conclude that our plants are resistant until they go through an entire process of several years in a field trial. So without completing this process of field trial, we don't declare that our material is resistant to the disease. The duration of the field trial is approximately between 85 to 100 weeks. Okay? Why? Because where we perform the field trials to reach the R4 cycle of fruiting, we need approximately 85 to 90 weeks. Nowadays, it's much more. Now we have the plants in the field for approximately 5 years. The next point is that we had to set up the field experiment in a good statistical manner. So the plants were placed in the field with controls, with controlled plants, in a way that we will be able to perform a good statistical analysis of the results. And finally, we had to perform some experiments to make sure that our labeling procedure or our tracking procedure goes all the way from the laboratory until the very end of the road, when we have the plants that we can declare that they are resistant. Okay, so many people ask me, why Gal? Why don't you take Granel? Why don't you take Williams? You know, they're more common. And we take Gal for various reasons. First of all, Gal is a variety that was developed by Rahan. Personally, I developed the Gal variety, and we are very proud of the Gal. The Gal has excellent traits for the export market. It has a very good yield. You can see just a few weeks ago, somebody from here, from Santa Marta, told me that on the average, he received in the R0, 28 kilograms per bunch. Gal has stress tolerance. That's very important, especially now with water deficiency and heat and so on. Gal has a quick return. That's very important to the grower. And the quality of the bunch is excellent. Anybody who grows Gal would realize how nice the bunch is. The bunch is cylindrical. The number of fingers is very high, and it has all the properties that you need as an export variety. The last point is that the Gal, being not too tall and not too short, it's a variety that is easier to manage compared to other varieties that are available to the grower. Okay, now here I want to apologize. I'm getting a little bit into the genetics. And I want to explain how did we devise the procedure that we are using, starting from the hypothesis that we had approximately 6-7 years ago, and all the way to the field trials and the selection of the variety that was made nowadays. So we used concomitantly two procedures that together they gave us mutations that I will explain a little bit more. So on one hand, we used chemicals that proliferated the cells that we use in tissue culture. So the cells divided very, very quickly. And not only did they divide, but they produced many meristems. Many meristems can be seen on the material that was introduced and was exposed to these chemicals or hormones that we applied in the tissue culture. At the same time, we applied another chemical that is called AZA. And what AZA does, just to make it simple, there are many genes in the genome that are not expressed. Why are they not expressed? Because they are hidden in the chromatin and they are not available to the components that aid the expression of genes. So using this chemical, what we did, we, in a sense, we freed this material, these genes from being inhibited of being expressed. We did this by a chemical mutagenesis that is called demethylation. When plants are methylated or when genes are methylated, they don't express. When we demethylate, we can express these genes. Now, in reality, we have, when we do this on the meristemoids that are proliferating, we have a very short window of time to do this demethylation process. And in this interim time, which is really just a few days in the development of the meristem, we have to demethylate, and then a few days later, methylation will reoccur and the plant will grow as a normal plant. But in this period of time, stem cells, the cells that give rise to the entire plant, when they had the opportunity of not being methylated, they produced a lot of mutations. So a lot of mutations were produced, and basically, in this diagram, I can show, and of course this procedure, we have patented it. So what we see is we created a library of plants, a big library of plants, approximately 12,000 plants. And these plants differ from one another very mildly. Just in a very small section of the plants, they differ. And I want to emphasize that this difference did not come from introducing nucleic acid or GMO as we know it in the literature. Okay? So this is a natural process that occurred due to the processes of using the hormones and the demethylation process. Okay? So the result is a large library of plants that are exactly the same, all of these plants, but they differ in one position in the genome. And in that position, if that position had to do with resistance to a disease, it's a bingo. Okay, so I'm not going into the details of this, but there are many ways of doing this. And the technique that we chose is the technique that is on the left side. And we are using retrotransposable elements. It's just a word. These elements are class 1 elements. For molecular biologists, they will probably recognize these elements. So these elements create mutations when they are demethylated in the stem cells. Okay, so we've done this. Now we have to prove that what we have is really resistance, and by the instruction of the board of directors, we had to prove that it's not tolerance, but it's really resistance. So how do we prove this? First, we use a molecular proof that I will show you. Okay. Secondly, we will show an ex vitro greenhouse inoculation experiment that I will show you also. The third point, we did a whole genome sequencing. So we sequenced the entire genome from A to Z, 600 million nucleotides. We have the data, okay? And we compared this sequencing between a resistant and a susceptible line. And we saw what was the difference. Of course, we performed the field trials, and the field trials were done in an infected area, and very soon we will do these field trials also here in the La Guajira area in Santa Marta area. The next component, we had to make sure, as I was instructed also, that the agrotechnical parameters will be useful for the trade market or for the export market of bananas. So all of these components of yield are very well known to the growers. If it's bunch weight, the number of fingers, cycling time, proper ripening, normal green life, and high Brix value, which is all fruit quality. So all of these were measured, and we made sure that not only we will have a resistant variety, but more importantly, that this variety will also be effective for the export market. This is the molecular proof. I'm not going to go into details. This is molecular biology, but you can see this is the mother plants, and these are the descendants from the same mother plants, and this is the time where we demethylated. This is this arrow, and you can see the two bands over here that are the results of demethylation. So this is a proof of a real mutation, okay? And this is the compound that we used. This is the AZA. Next, we have to prove that the system that was used by Fernando Garcia in Kema's laboratory is a good and reliable method to show the difference between resistant and not resistant plants. So Fernando performed an experiment. This is an AD, which is a Rahan clone, which is a regular Cavendish. So it is very susceptible to TR4. And you can see that using when they were inoculated, they got infected. Also, Granen was infected. It's another Cavendish. And Gros Michel is also susceptible to this disease. When we used race 1, we saw that only Gros Michel was infected and the two Cavendish were not infected, as expected, of course, as in the literature. And this is the control of the water. This is the greenhouse at the University of Wageningen in the Netherlands. Okay, so these are the results, and I have to thank Fernando for performing the screening. And the results showed that out of almost 10,000 plants, we got 415 lines that were, at this point I don't call them resistant, but they were asymptomatic. You don't see any symptoms. So here's the symptoms that you can see on the majority of the plants, but the small subset of the population is asymptomatic. You can see no symptoms on the plant. Are these resistant? We will see in the field. Okay, next step is the field trial, okay? In the field trial, we again validated that what they did in the University of Wageningen was a pretty good job. okay? The job was done very well because we got 99.5% in one field of the plants were resistant to the disease, and in the other field, 96.9% were resistant to the disease. But yet, it's not 100%. And our aim is 100% resistance. So we used lines that in 120 plants that were placed in the field, not even one was infected with the disease. Not even one. If one plant was infected, we discarded the entire line. Sorry. So the next point was to make sure that the fruit looks nice, okay? That it looks like a gal. And actually, it looks exactly like a gal. Now, I just want to show you that the lines that we chose in the field were surrounded by controls that all got infected with the disease. So we only chose lines that not only 100% of the plants survived and had no symptoms, but all the plants around them in the field, that's the red dots, were all infected. These are the agronomical parameters, and you can see it's exactly like gal. We compared it to gal, and there is no difference whatsoever. This is the most striking photo that I have. Actually, I could have done the whole lecture here, but just showing this photo. So this photo was taken about 6 weeks ago by a colleague of mine that went to the Philippines. And as you can see, on the right side is the resistant line, and on the same field, on the left side, is the lines that are infected. It's Williams, regular Williams, that are infected with TR4. Not even one plant on this line, on this side, is infected with TR4. Not even one, okay? So here, we finally, this experiment is already 5 years old. So we concluded here that we have a resistant gal. Only after 5 years, this was our conclusion. Next, we went to the genome analysis, and we found that these retrotransposons are very close, they are in close vicinity to a cluster of resistant genes. I'm not going in details again about the molecular biology and the functionality of resistant genes, but these are genes that are responsible for resistance. Our conclusion that these genes were silenced before we demethylated the DNA. Okay, here we went to a second direction in the project, and this is thanks to our friends and colleagues from TechBaco. And back a few years back, more than 5 years ago, they engaged us in a project where they wanted us to get Valerie to be shorter, because Valerie is, as you all know, is a very tall variety. So they asked us, because they liked the Valerie very much, and they asked us if we can make it shorter. In light of the success of making the Valerie shorter, and we really made the Valerie shorter, these are the people, Miguel Lamos and Fabian and Rosa, so everybody knows them, and we did it right here. So we not only got the plant shorter, but we got yield that was even better than the normal Valerie. So our next task is to go back to the laboratory and develop a resistant line from this short Valerie to do exactly the same protocol that we used in the gal. But this time we were a little bit more clever, and we said to save time, we will plant 2 plants per pot. And we will choose only pots that one plant is infected and died, and the second plant is not infected and is asymptomatic. Because this way we have a better assurance that the plant that is not infected, it's in the same pot. You can't say that it's an escaped or it was escaped or anything else. So there is a better assurance that our plants are really resistant to the disease. So we passed that. And now we are just on the verge of performing the work in La Guajira. The plants are now in the hands of ICA. They are performing the quarantine process. And once we finish the quarantine process, we have still a road to go in La Guajira, but in the Philippines, we already have 3 fields, and the third one right now has 60,000 plants that all look good for over 2 years now that we have this experiment. So finally, I just want to acknowledge with thanks all the people that were engaged in this development. So first, I would like to acknowledge my fellows in Rahan Meristem. I speak to you, but they do the work, so they deserve more than me. I would like to acknowledge and thank Mr. Luis Alberto Restrepo that he supported the project of the GAL. We are really grateful to Banarica and Mr. Restrepo for supporting us, and he continues to support us on this. We also got very good support from Tecbaco and Banacol that also gave us support. Riyad Kadavid, an old friend of mine, always supported my research, and we were very good friends forever. The University of Wageningen for performing the first screens in the greenhouse, the inoculation. Unifruti is the company in the Philippines, in Bukidnon. It's an area in the Philippines where there is a very heavy infection of the disease. And finally, Mr. Yanai Nir, who is the CEO of Meristemos Colombia, who did a big chunk of the work, especially on the Valerie, and Mr. Hillel Kokotek in Rahan Phil, who is our CEO in Rahan, Philippines. Thank you very much for your attention.